Dear students, in the last class we discussed the H parameter model for our transistors. Now I would like to tell you the H parameter model for our different configurations, common base, common emitter and common collector configurations. So for that, the generalized equations are V1 is equal to HI times I1 plus HR times V2 and I2 is equal to HF times I1 plus HO times V2. The first equation is telling about the KVL, the second one is KCL. So you can draw the circuit like this, a resistance in series with a voltage source at the input side and a current source in parallel with a resistance at the output side. So let it be this voltage V1, the current through this one is I1. So this is HI plus and minus HR times V2 and this is HF times I1 plus HO. This is the output voltage V2 and the current in this one is I2. So this is the generalized model. So in the generalized model, this voltage source value is HR times V2. That means the output voltage. If you take this current source, it is HF times I1. This I1 is nothing but the input current. So now I would like to write this model for different types of configurations. The only thing is you have to understand what is the input voltage, what is the output voltage, what is the input current and what is the output current for every configuration. So let us see the first configuration here. This is CB. In the CB configuration, just you take this CB, that means the base is common, emitter is the input and the collector is the output. So what is the input current here? IE and the output current is IC. Input voltage is VGB, base is common here, base is grounded. So VGB, this is plus and minus. And what is this output voltage? VCB, this is plus and this is minus, this is VCB. Once you know this, just substitute here. So what is the input current here? Input current is IE because I am drawing for the CB configuration. So IE. What is the value of this voltage source? HR times output voltage. What is the output voltage here? This is plus and minus. The output voltage is VCB. So the value for this one is HR times output voltage. HR times VCB. And the current source value is HF times the input current. What is the input current? IE. And this is the output current. Output current is, you can say, the collector current IC. So as you are drawing for the common base configuration, the H parameters also should be converted for the common base. So I can use here HIB, this is HRB, HFB and HOB. Now your H parameter model is ready. Your H parameter model is ready for the common base configuration. The only thing is you have to write down the input voltage and output voltage, input current and output current perfectly. So this is for the common base configuration. So for analyzing purpose, as usual, you can just connect a voltage source here. This is the input Vs in series with the resistance Rs. This is plus and minus, this is Vs. And for taking the output, you connect a load here. This is RL. And the current through this one is, let us say, IL. So if you just evaluate and if you do the analysis of the circuit for the current gain, input resistance, voltage gain and output admittance, the generalized equations will be coming here. Already we have developed the generalized equations for your current gain, voltage gain. What is current gain? Current gain AI is equal to minus HF by 1 plus HO into RL. HO into RL. And what is the input resistance RI? RI is equal to HI plus AI into HR into RL. What is the voltage gain? Voltage gain AV is equal to AI into RL divided by RI. So these are the generalized equations already we developed in the last class. Here what may be the difference here? Whenever you are drawing this, whenever you are calculating these parameters, it may be AI is equal to minus HFB by 1 plus HOB into RL because it is for common base. So, like this, other parameters also you can do this. So, I already told you very clearly, whatever the expressions I derived in the last class, those expressions are equally valid for all the configurations. That's why you can utilize this. So, this is the way of drawing the diagram for your common base. Okay, let us see this most popular circuit, that is common emitter. In this common emitter, let us say once again to avoid the confusion, this is common emitter. Emitter is common here, and the input is the base, and output is the collector. Input current is IB, output current is IC, input voltage is VBE, and output voltage is VCE. Simple. Just note down all these values here. What is the input voltage here? This is VBE, this is plus and minus, and the input current is IB, and you can say HR times output voltage. What is the output voltage? VCE. And this is the current source, HF times input current, that is HF into IB, HO. What is the output voltage here? This is VCE. And the output current is IC. So, this is the way of converting the generalized configuration into the common emitter configuration. Here also the same thing. You have to just convert your H parameters for common emitter configuration. So, HI becomes HIE, HRE, HFE, and HOE. Simple. This is the way of writing the H parameter model for your common emitter configuration. I can say whatever the diagrams I have given here, all these parameters it is called as exact model. So, this H parameter model is an exact model because everything we are taking care of. In the later stages, we are going to discuss the simplified model also by avoiding this voltage source and this HOE. So, we will discuss it later. So, exactly like this, for the common collector configuration, collector is common. So, collector is grounded and base is the input and output is emitter. So, input voltage is VBC, output voltage is VEC, and the input current is IB, output current is IE. Simple. So, what is the input voltage here? The input voltage is VBC. This is plus and minus, and the input current is IB, HR times output voltage, HR into VEC, and HF times input current, HF times IB, and this the output voltage is VEC. The output current is here, this is IC, output current is IC. So, exactly, in order to convert into your common emitter configuration, the H parameters also can be converted HIC, this is HRC, HFC, and HOC. So, this is the model for common collector configuration. So, this common collector configuration is also called as emitter follower. Why it is called emitter follower? Because the output follows the emitter. Common collector configuration means you are taking the output at the emitter. Emitter follows input. That's why it is called as an emitter follower. So, if you take this common collector configuration or common emitter configuration or common base configuration, this is the way of drawing the exact model of H parameters. So, for all these things already we have developed these expressions for the general circuit. So, these expressions are equally valid for all these configurations. The only thing is you have to use proper notation for different configurations. Suppose for example, if it is for common emitter, you can say minus HFE by 1 plus HOE into RL. This is HIE plus AI into HRE into RL. AV is equal to AI into RL by RI. So, like this, you can draw the H parameter model very easily if you know the procedure of drawing the H parameter model. Okay, I hope you understood this. Now, let us analyze, let us see the calculation of H parameters from the characteristics also. How to calculate these H parameters from the characteristics? The reason is, whenever you are buying a transistor, the manufacturer is going to give the details of all these H parameters on the manufacturer sheet. These H parameters are very much essential to calculate the properties of all these transistors. So that is the reason let us understand how to calculate these H parameters from the characteristics, because sometimes the manufacturer is not going to supply the details of H parameters, but already we are doing the experiments, common emitter, common base and common collector characteristics. From those characteristics we are going to calculate the H parameters. So that thing I would like to explain it now. Now we are going to see the evaluation of H parameters from characteristics. Already we have drawn the input characteristics as well as output characteristics for the common emitter configuration in our laboratory. So I would like to evaluate the values of HIE and HRE from input characteristics. So what is the relation related to this? The general equation is V1 is equal to HI times I1 plus HR times V2 output voltage. So for common emitter configuration, what is the input voltage? VBE is equal to HIE into IB plus HRE times output voltage is VCE. So how to get this HIE value? HIE is equal to VBE divided by IB. At that time your VC is constant, VC is 0. So that's why you have to make it constant. So similarly, what is HRE? HRE is equal to, the reverse voltage gain is equal to VBE by VCE. At that time input current is constant, IB is constant. Okay. So this is the generalized definition for your input impedance as well as the reverse voltage gain, that is HIE and HRE. Now I would like to explain how to calculate this HIE. What is HIE? HIE is nothing but VBE by IB and for different values of VCE. So that's why here these are nothing but the input characteristics VBE versus IB for different values of VCE. So here the VC is constant. So let us take one VCE. So let us take this VCE 3 and consider the points 2 here. There are 2 points we consider and elongate to the x-axis, and this point is also along to the x-axis. Let us say this is A and B and this difference is delta VBE. Delta VBE. Similarly, extending to this y-axis. This is y-axis means it is telling about the current axis. So this difference is IB2 minus IB1. So I can say this is IB2 and IB1. This is delta IB. This is delta IB. Now if you take the ratio of this delta VBE by delta IB, you are going to get your HIE. So here I can say HIE is equal to delta VBE divided by delta IB, approximately equal to delta VBE by delta E. This way you have to calculate your HIE. Similarly, you can calculate the value of HRE from this input characteristics. HR is the ratio of VBE to VCE, IB is constant. Let us take this IB constant and take a line here. So it is cutting this at this point and at this point. So the difference is delta VCE, delta VCE. If you are taking the projections on the x-axis, you are going to get your delta VBE. Then take the ratio of delta VBE to delta VCE, then it will be equal to HRE. So HRE is equal to delta VBE by delta VCE. Change in base to emitter voltage divided by change in collector to emitter voltage. So this way you are going to calculate your HIE and HRE from the input characteristics. Similarly, I would like to tell you how to calculate HFE and HOE from the output characteristics also. What do you mean by this output characteristics? It is a graph plotting between output voltage versus output current, keeping input current as a constant. So I would like to write the one more equation for this, like the generalized equation is I2 is equal to HF times I1 plus HO times V2. This is the generalized equation in H parameters. So for CE configuration, what is I2? IC is equal to HFE times IB plus HOE times output voltage is VCE. Then What is the definition of HFE? HFE is equal to IC by IB. That means change in the collector current divided by change in the base current. Keeping VCE constant. VC is equal to constant. Exactly, that's the reason. Try to write down these smaller letters here. Smaller letters indicating, very small letters indicating the changes in the currents here. So that is the notation you have to use. Exactly, HOE is equal to change in the collector current delta IC divided by delta VCE. At that time, IB is equal to constant. So you know the definitions of HFE and HOE. What is HFE? Forward current gain. What is HOE? Output admittance. So now coming to these characteristics, how to find out this HFE? Delta IC by delta IB. Now let us take a point on any characteristics. So this point you take the characteristics. So this is IB. And one more IB is this one. So this difference is indicating this is delta IB. Just take the projections on x-axis. This is the projection. And you project like this. So the difference is delta IC. So you take the ratio of delta IC by delta IB, because at a particular point of VCE, you are taking these 2 points. VC is constant here. So I can say HFE is equal to delta IC divided by delta IB. So in this way you have to calculate this forward current gain. Exactly, for calculating this HOE, what to do? It is the ratio of delta IC by delta VCE. So you can say delta IC. You try to take a point here. You point on any characteristics. Let us take that. You take a point here. This is. And one more point you try to take here. It is having some slope. So if you elongate like this, and one more, this one is like this. So this will give you delta IC, and you project onto the x-axis, and this, you are going to get delta VCE. So you got delta IC and delta VCE. Therefore, HOE is equal to delta IC divided by delta VCE. At constant IB, because IB is constant here. On the same characteristics of IB, you have taken the 2 points like this. So in this way you are going to calculate your HOE. So very simple, friends. Two H parameters can be calculated from the input characteristics, another 2 from output characteristics. If the H parameters are not given by the manufacturer, just do the experiment in your laboratory, get the characteristics. From the characteristics, you are going to calculate all the 4 H parameters. So I explained for the common emitter configuration. The same analysis can be applied for the other configurations like common base and common collector configurations. Okay. Up to now, we have seen the analysis of all these circuits using H parameters, and definitely we can conclude that H parameters are very much convenient to analyze the transistor circuits. So finally, I can say what are the advantages of the H parameters? H parameters are the real numbers at audio frequencies. They are not imaginary, they are real numbers. Whenever they are actually calculating these H parameters, they are also taking care of the temperature variations. That's why they are very real numbers at audio frequencies. Very easy to measure. Just now we have seen the measurement of these H parameters from the characteristics. Even in the laboratories also, they are going to estimate these values very easily. We can measure it. They can be obtained from the characteristics. And once the H parameter is known to you, it is very much convenient to use in circuit analysis. Because in the electronic circuit analysis, if you want to analyze any transistors, then definitely you have to use the H parameters. The transistor model should be represented by the H parameter model for getting all these parameters. So, very convenient in circuit analysis, and they are very much useful in designing, and most of the manufacturers are very much particular to specify the H parameters, because H parameters are going to decide the design of the circuits. That's the reason H parameters are very, very important. So, once you know these H parameters, then once again I would like to tell you remember all these formulas. These formulas which are having these H parameters, current gain, input resistance, voltage gain, output admittance, current gain with source, voltage gain with source. All these formulas are equally applicable for all types of configurations. What are the configurations? Common base, common emitter and common collector. So for all these configurations, happily you can utilize all these formulas. But the thing is, sometimes in your problems, the problem may be given for the common emitter configuration, but he is going to give the H parameter for the common collector configuration. Then what to do? Then definitely you have to convert from one configuration to other configuration. So that's the reason you try to see this table. This table is indicating the conversion formulas. It is indicating the conversion from one configuration to other configuration. If you see it clearly, the first one, it is telling about the relation between common collector to common emitter configuration. HIC is equal to HIE, HRC is equal to 1, HFC is equal to minus of 1 plus HFE, HOC is equal to HOE. So, it is relating the H parameter for the common collector configuration to common emitter configuration. Suppose if the problem is given in the common emitter configuration and he has given H parameters for the common collector configuration, then definitely you have to convert from one configuration to other configuration, and after the conversion you can substitute all these H parameters into those generalized equations. Whatever the equations we have developed for the current gain, input resistance and voltage gain. So similarly, if you take this table is telling about the conversion from common emitter to common base, common emitter to common base. So HIB is equal to HIE by 1 plus HFE, HRB is equal to HI into HOE by 1 plus HFE minus HRE, HFB is equal to minus HFE by 1 plus HFE, HOB is equal to HOE by 1 plus HFE. So here what you have to remember is, in the denominator always you are having the same factor. It is easy to remember. So once you do the practice, definitely within no time you can convert from one configuration to other configuration. So this table is telling from common base to common emitter. If you know the conversion formulas, the problem may be done within the stipulated time very easily. So this way, try to remember the conversion formulas and as well as the generalized equations for calculating your current gain, input resistance and voltage gain, and you should know the importance of the H parameters also. So I hope you understood the importance of the H parameters and its use in analysis of all our transistor circuits. Okay, thank you.